Okay. This week's lecture is going to happen in a handful of parts, and I encourage you to watch them in order. This is part one. We're going to start our discussion of a very particular kind of motion. It's not quite linear motion in the sense like chapter 2, chapter 3. It's not quite circular motion either. It's a motion that we haven't yet talked about. And it's our discussion of motion that repeats itself. For example, motion that repeats regularly with the same time interval between repetitions. In other words, with a period, a definable period between cycles. We can call it periodic motion as opposed to oscillation. Okay. It's one-dimensional motion, or at least this example is, but it's motion, again, that repeats itself. This is kind of different than the motion we used to look at back in chapter 2, chapter 3, chapter 4, I suppose. And it's different still from the motion that we talked about in the rotational chapters as well. So I'm not really sure how to describe, if we think about the end of the slinky moving up and down, I'm not sure how to describe its position as a function of time or its velocity or its acceleration. So I guess I'll start with the same thing we kind of always start with here lately, and that's Newton's second law. Let's talk about the situation. We've got a spring, and for the sake of argument, let's make this a spring that has a mass attached to the end of it, where the mass is much, much heavier than the spring itself. So like the mass of the spring doesn't really matter. It has some spring constant, K, but it's this mass that's stretching it down. If we gently hang the mass and allow it to find the point where it rests, then what we're talking about is equilibrium. Position of equilibrium. That's the position such that the sum of the forces is equal to 0. In other words, the mass times g of that mass that's hanging on, the gravity pulling the spring down, and the elastic force pulling the spring back up. Let's say that it's some position R equilibrium minus some original position R0. So we could find an expression for the equilibrium position in relation to some initial R0, and here's R sub EQ. Okay, that's fine, we can do that. So let's see, if we move that to the other side, divide by K, and G over K, R minus R. And if we put R0 on the other side, then we've got an expression that is the equilibrium position. Okay, what if we stretch it past that and then let go? Well, that'll, the spring will be stretched more than in equilibrium, so the net force will be up. It'll go through equilibrium, and because at that point, we'll have some velocity. And we'll go past that equilibrium point because at that point the net force is zero. We haven't stopped yet. We need to be past equilibrium, shorter than equilibrium length, so that gravity is stronger than the spring and tends to slow down our upward motion. So we'll go past equilibrium up to some point, and then we'll fall again because the spring isn't stretched enough to hold us up. Then we'll fall through equilibrium and back and forth, and we'll get that oscillating, oscillatory motion. Okay, so what about some point down here, some just some R, some new position R that we drag the mass to and then release it? What's the story at some position R? All right, well, I'm going to keep that, but at some other extension that isn't at equilibrium, we can solve Newton's second law, or at least we can write it. The sum of the forces should be the mass times the acceleration. Now, the sum of the forces, all right, we've got the spring, K, our new place, minus the initial length, right? Because that's how far we're stretched from original equilibrium. Mass times acceleration. Now, I'm just going to call this how far away from the actual resting point of this loaded spring are we at point R? I'm going to call it A. I just need a letter for it. So this R is A plus REQ. But REQ, we had an expression for it. K A plus was mg over K plus R0 minus R0. Okay. Fine. So the R0s are going to cancel. We can multiply through Ka plus Mg equals Ma. Now, this capital A is a function of time. It can change, as we get, after we release the mass, it's pulled up, and so A decreases and then becomes the other side. So can I call this like position Y or something? Oh crap. Why crap? Because the acceleration of that mass, acceleration is, well, I mean, I guess it's the rate of change of the rate of change of position. So if we write it in derivatives, it's the second derivative of the position, and now we've got our y coordinate equated to its own second derivative. This is a second order differential equation in y. And I'm not really sure how to solve that. we start to wonder, is there something that makes us think about this kind of motion if we only look at a certain section of it? Is there something else that we can appeal to? Oh man, that lets us sort of see through what's going on here and allow us to talk about, a function of time for the position of this mass. I'd like to talk about Plato. I couldn't resist this joke. No, I don't want to talk about Play-Doh. I want to talk about Plato. If you're familiar, if you've maybe read, the last days of Socrates, some of the Platonic dialogues, you might already be familiar with the allegory of the cave. And the story is, at least in philosophy, that the pursuit of knowledge and enlightenment, that we start out our lives as the prisoners here behind the wall, chained, constrained to only look in one direction, at the wall where we see, our reality. We look at the wall and we see the shadow of a horse, and we say, "Oh, that's a horse. That thing there on the wall, that's a horse." But it's not actually, right. The actual horse is here, and is what we're seeing is just a shadow, just a mere shadow of something truer. That the reality we see around us is only a shadow of something truer, something more pure, more enlightened, in a sense. um, that there's you know some platonic form out there of horse, that all of our terrestrial, all the horses that exist are sort of participating in the idea, the form, the platonic ness, the beingness of horse, the true sort of real horseness. And we are only able to see, the earthbound, the sort of shackled, the manacled sort of interpretation of horse. The rest of the allegory, the rest of the story goes that we should strive to free ourselves from the chains of the constraints, and observe the rest of reality, and encounter the sunlight, and stagger blinking into the knowledge of what is true. And at least that's the goal. And then our job then is to, well, I don't know if it is a job that we want. I think in the actual story, the our enlightened individual here goes back into the cave to try to help, the fellow prisoners that are still sort of stuck looking at only at shadows, and they the prisoners that are still there, I think, end up um, you know attacking the our recently enlightened individual, um, for too drastically challenging their worldview. Um, but it's portrayed as a duty that we have to, once we've shaken off the chains and realized the trueness, and the like baseness of our perceptions about this world, and that it's only sort of participating only a little bit in something truer, something more real, that it's incumbent on us to try to share that, even at the risk of ourselves. What does that have to do with anything? Um, we've talked about rotation. We've talked about circular motion, rotational motion. We have uniform circular motion and the centripetal forces that permit it, and we've talked about angular position, velocity, acceleration, theta, omega, alpha, and we can describe rotational motion pretty well at this point. I'd like you to imagine that you had a thing undergoing uniform circular motion with some angular velocity, omega, some object. And as it rotates around a circle at some radius, r, as it rotates, imagine that you had above my whiteboard here, shining down, imagine you had the Platonic light, the fire in the cave, shining on these objects that our performers are walking by and making the shadows we see. So suppose off the top of the screen here, there was this fire in the cave shining down on our circular object, circular motion, and that there was a screen here, a wall in the cave on which there was a shadow projected. The light shines down and the shadow of the object shows up on the wall, and we can see this. As the object moves, the shadow moves back, and so it moves to the left as this moves around, and then it starts to move to the right again, and then it starts to move to the left again, and the right again, and the left again, and the shadow just moves back and forth. What if oscillation is just a Platonic shadow of a truer circular motion? What if circular motion will allow us to describe one-dimensional periodic motion? I don't know how convincing this is with the whiteboard drawing. So I have a series of videos that I'd like to play snippets of for you. I'm just going to keep sharing my screen this way. This is the first one, and it's quite short. But what's going on? This is a motorized rotator, and this is a mass bouncing at the end of a spring. And as you can see, they follow each other. But the rotational motion of that object viewed end on, again, viewed end on, just looks like oscillation, the motion of the mass up and down. Sorry about that squeak. Here's an animation, a simulation, something a little bit sort of nicer to look at and listen to. So we've got this oscillation that we're considering, but what if we imagine that it is just a projection, just a shadow of full circular motion? We have this object undergoing circular motion, and if we view it end on, or in other words, if we shine light and cast a shadow, it just looks like oscillation. And here's an animation coming up of this sort of shadow idea. If we make a shadow on a wall, a projection of this object, then we're describing, well, or at least we're sort of representing oscillation in one dimension as a projection, as like a component of circular motion. We know the functions that tell us a component of circular motion. We've known that since pre-calculus. The component that we are talking about from the origin across is just the x-coordinate of a point of intersection with a circle. We know how to find that x-coordinate. It's, well, as long as we know the angle, then we know that that x-coordinate is huh. Wow. Here's another video. We've got a record player turntable with an object on it, and this dot is motion tracked. It's motion tracked to the video, and if we isolate just one direction, just one component of circular motion, we can see if we plot those points as at time intervals, take a series of little frame snapshots and connect them all, we're going to see a trigonometric function just like we expect. If it is a circle, then we know how to describe that little component there, and it's trigonometric. And we're watching a trigonometric function show up before our eyes as we motion track that dot that represents that object moving in circular motion. Okay. So the story is that we're going to let circular motion stand in, sort of be our model for oscillation in one dimension. All right, so now we have to unpack exactly what that means, and I'll stop part one here, and I'll pick up from here in part two.